All right, so the next chapter is all about acid-base chemistry. Arguably, this is one of the most important reactions that you'll run into in organic chemistry. It's the fastest reaction in chemistry. It's the reaction that takes precedence over all other reactions when in competition. There are two main types of acid-base chemistry. And ironically, they were both developed in 1923. Does anybody want to help me remember what those two names are for the theories? Bronsted-Lowry are the main contributors to the first one. And they describe the movement of what? Protons. So when they were looking at acid-base reactions, they were always looking at where protons were moving to and where they were moving from, right? It's important to remember that H plus is a proton. It's not a hydrogen atom. A hydrogen atom has electrons with it. A proton does not have any electrons. All right? The competing acid was by who? Or whom, I should say. Lewis. Who is Lewis? He described the movement of electrons. Really, these are two sides of the same coin. They're both looking at the exact same phenomenon. However, Lewis's theory was much broader and all-encompassing, where Bronsted-Lowry is a bit more narrow. However, organic chemists, when they're looking at these theories, are primarily talking about the Bronsted-Lowry acid-base definition. So let's start with that. And this might be review for a lot of you, but I figured it'd be good to have a refresher. So let's go ahead and define this in a bit more detail. In Bronsted-Lowry's definition, does an acid donate or accept protons? Donates. Do you have a question back there? Yep.
So, is there a big difference between the protons moving and the electrons moving?
Yes, and we'll get into that, especially when we switch back into Lewis theory. Lewis theory is very broad. Bronsted-Lowry acid-base theory is a subset of Lewis acid-base theory, so it's much more limited in scope because we can only look at movement of protons. Yeah. So Bronsted-Lowry said that acids donate protons. And bases accept protons. And it's a pretty general theory, and I like to show this using a pretty generic acid-base reaction. So we know that in this case, this is going to be our acid. It's got a proton dangling off of it. And this is going to react with my base, which I'm going to describe as B with a lone pair. And under most conditions, you can think of this as an equilibrium reaction. However, we'll talk more about that later. It depends on the strength of the acid or the base. And this base can actually reach over, grab this proton, and we show this with arrow pushing notation. We'll practice this more later. And then the covalent bond between the proton and the acid gets kicked over onto A. All right, so now we've got a covalent bond between the proton and our base B. And what charge should B have if it gave electrons to the proton? Positive. Okay. And over here we'll have A. It got both electrons from the covalent bond, so what charge will it have? Negative. So it'll be formally an anion. All right, if we think about Hb+, this is referred to as a conjugate acid or base? Ah, it's tricky. Conjugate acid, because now it has the proton. It in many ways can now act as the acid, right? So Hb will be the conjugate acid, where A- in this case will be the conjugate base, because now it can have a negative charge or a lone pair to donate back and steal a proton. So it's important to remember this is technically in equilibrium. However, one side of the equilibrium can be favored over the other. There's two main things I want you to really remember from this. The first one is that strong acids create stable conjugate bases, and strong bases create stable conjugate acids. It's a pretty simple trend. It's easy to overlook. It's easy to not really understand why, but we're going to spend a fair amount of time getting into that in the next section. But before we do that, I want to start defining equilibrium constants a bit more, since I know some people have forgotten those. So let's define the equilibrium. And if you think all the way back to Gen Chem, we can rewrite out this equation. Actually, I'm going to change this. I apologize. In this case, we're going to show it as an acid mixed with water. And in this case, what two products are we going to get out? Are we going to form hydroxide? In this case, the acid's going to donate a proton to water. So water will now have an extra hydrogen on it. And what formal charge? Positive. So is this our conjugate acid or conjugate base? Conjugate acid. And then over here, we should have our conjugate base, A minus, right? So we can think of this as our generic acid dissociation in water, right? So if you mix an acid, any acid in water, it will dissociate into the hydronium ion plus a conjugate base. Okay, so if we define this as an equilibrium, we'd say KEQ equals concentration of the hydronium ion times the concentration of our conjugate base over the concentration of our acid. Oops. Plus the concentration of water. Oops, sorry, that should be times, not plus. Holy cow. All right, so this is at equilibrium conditions. You've got this ratio of products over reactants, right? However, most chemists will take this water and multiply it out. So multiply water on both sides, the concentration of water, and you get a new constant, which is KEQ times the concentration of water will now be equal to the concentration of the hydronium ion times the concentration of your conjugate base over the concentration of your initial acid. Does anybody know why you do this? You remember?
Yeah, it's the water is constant and it's pure.
Yeah, the water's in such excess, the concentration really isn't changing much. The concentration is huge. So in this case, we're going to pull it out onto its own side. But then the nice thing is, what we do is we condense this down into its own unique term, and we call this a Ka. And now, we can simplify things, ignore water because it's now factored into the Ka. And we've got our acid underneath. This is super duper important in chemistry, right? Hopefully you remember this from Gen Chem. It's just simple equilibrium conditions. All right, this is referred to as our acid dissociation constant. And this is really heavily used specifically by organic chemists. All right, let's practice our math skills. Large Ka If you have a really large Ka value, is your acid strong or weak? Strong, right? If it's really, really large as a number, that means you've got a really large numerator. That means you've got a lot of hydronium in solution. So large Ka equals strong acid. All right, a small Ka, on the other hand, means that you have a weak acid. This is one thing I love about organic chemistry. We can boil math down into these really simple terms like that, right? All right, so let's take a look at a few examples. Let's consider HCl plus water. And in this case, I'm actually going to draw out the Lewis structure for each of these. And we've got these equilibrium arrows. We know HCl, by its very name, hydrochloric acid, is going to be a good acid, so it's going to donate its proton to water. Another way of thinking about this, too, is water, being the base, is going to steal the proton. So we can show this with arrow pushing. Water, in this case, is going to grab this proton. The bonding set of electrons is now going to get dumped over to chlorine. And our conjugate base, in this example, is going to be chlorine with the negative charge, plus our hydronium ion. Classic, easy example. If we think about HCl, why do we consider it a strong acid? 100% dissociation. And if you remember back up here, I said strong acids create stable conjugate bases. Let's take a look at the conjugate base. Over here, we've got our conjugate base. Why is this conjugate base so stable? It's got a full octet, and what about its electronegativity? It's pretty electronegative. It's in that top right-hand corner of the table. It's perfectly happy having a negative charge. So that's another way of thinking about why HCl is a strong acid. Yep?
Would it still have double arrows if it's a strong one?
That's an important question. So the question is, would it still be considered under equilibrium if it is a strong acid? Occasionally with strong acids, you'll see a single-headed arrow because the product side of the equilibrium is so overwhelmingly favored that really there's such a negligible amount of reagents left that they're almost non-existent, so why worry about them? So sometimes you do see strong acid shown with a single-headed arrow. And I'll talk more about when to kind of assume that it's single-headed versus double-headed. Yep. So let's think about the Ka here. So if we try to express this, we can say, all right, it's the concentration of our hydronium ion times the concentration of our chloride anion over the concentration of HCl at equilibrium, right? And if you plug this in and look it up, it's going to be a Ka of about 100 million, so pretty big number. All right, now let's take a look at a different example. This example, we're going to look at something pretty similar, so acid-base reaction. Yep. So Ka is unitless because it's a ratio. Yeah, that's a good question. All right, so the next one, we're going to look at methane. This is natural gas, stuff you use in your furnace at home. And you can think about methane reacting with water. Okay, in this case, we're going to treat methane as the acid and water as the base. Bear with me. So it's going to steal one of those protons off of methane. And we can show the equilibrium arrows. All right, now we've got our conjugate base. So we'll write that down. And we've got our conjugate acid. Is our conjugate base stable? Heck no. Chlorine is not electronegative. It is not happy with the negative charge. So in this case, do you think the product side of the equilibrium is going to be favored at all? No, practically none of that is going to be made, so the equilibrium can be thought of as favoring the starting material side, not that product side of the equilibrium mixture. So let's go ahead and just for the sake of argument, write out the Ka expression. All right, so now we've got our conjugate base, conjugate acid over CH4. You can actually calculate this and look it up. And if you do it, you've got 0.000000000. My hand might get kind of tired, so I'm just going to put dots there. There are 48 zeros here. Another way of thinking about this is the likelihood of water deprotonating a methane molecule is the likelihood of somebody hiding one atom on planet Earth, one atom, and you finding it. It's not very likely to happen, right? So in this case, it's not an acid-base reaction we would typically draw, but we can show this with numerical values. Yep?
What you're saying is, if you had some of that conjugate base, so you're like the strongest base in the whole world.
Yeah, so the question was, if you have this conjugate base, if it's really unstable, that means it really, really, really wants to steal a proton back, and it's a wickedly strong base. We'll talk about some of these exceptionally strong acids and bases later. Yep?
So if it's going to be a strong base, if we drop the strong base and is it going to install a proton from our body?
Yeah, so for example, if you have a base with a carbon that has a negative charge, and you spill it on you, instant chemical burn. It'll immediately rip protons off of whatever it can find. And acid-base chemistry, in addition to stealing protons, generates a lot of heat, so you'll have a heat burn as well. Not super fun. We avoid these if possible. Yep?
How much over 14 is the
So in this case, we're not really looking at pH. We're looking at something entirely different. pH, if you think about it, is negative log of the hydronium concentration. It's measuring something else. But that leads me to my next point, something closely related. If we think about this, we're looking at numbers ranging from hundreds of millions to numbers so close to zero that it makes your hands cramp writing it out. So we need a better system of doing this. And instead of writing them out as these giant, big, or small numbers, we use a system of P units, or pKa. So pKa helps to narrow down this large range. Of Ka values. All right, and it's important to think of P as a mathematical unit. What does P stand for in math? Think about pH, it's negative log, right? So pKa is going to be equal to negative log of your Ka unit, right? All right, if we think about this in another way, small pKa values indicate a strong or a weak acid. Super strong, right? So it's kind of flip-flopped. Big pKa equals a weak acid. All right, so let's go back up and look at these numbers that we had. And let's try to assign a pKa value. What's negative log of 100 million? Not everybody all at once. Did anybody have a calculator and want to check? No. Like, we just did a quiz. What is this? I was promised no math. -8, right? So -8. That's a pretty small number that indicates that hydrochloric acid is a very strong acid. All right, let's go back down. Let's consider this one with 48 zeros.
Are there any other numbers
So in this case, we're just focusing on the zeros because we're thinking about orders of magnitude, essentially, right?
Log doesn't care what number it is.
Yeah, log doesn't care what number it is. We're just looking at order of magnitude. If we look at this one, this would be a pKa of 48, right? Oop. All right, that leads me to my next very important point. Now we're in a smaller range, typically going from about like -10 to 50. That's manageable. My big takeaway from this is the difference in I can't talk today. The difference of 1 pKa unit is an order of magnitude, meaning times 10, right? So oftentimes in organic chemistry, I'll hear students say, well, the acidity is pretty close according to the pKa table. One's a pKa of 3 and one's a pKa of 5. And I'll be like, yeah, that's like saying you're 100 times stronger than me. That's not at all comparable, right? So we have to be really careful. Even though you have these small unit increases, they're really significant. An increase of 1 means it's 10 times as powerful as an acid. So we do have to be extra careful when we're dealing with pKa units. Does that make sense? All right, I think that's where we're going to stop today. For the problem of the day, it is a little bit tricky. I want you to draw out what the conjugate base for each would look like, and then ask yourself which of the conjugate bases is going to be more stable than the other and why. Think about it. All right, I'll see you tomorrow.